We're going to explore vector valued functions because they behave almost exactly like parametric equations for most of the purposes and intents of our course here. I would encourage you to make sure that you review vectors on your own. I will link a couple of videos I have on vectors and how they work. But let's just do a quick breakdown and review of vectors in a plane. So if you recall that a vector is a representation of both direction and magnitude, that's what a vector tells us, not only how far something has gone, but also the direction in which it has moved. So every vector has what we call an initial point and a terminal point. So let me just plot both of those here. So if my initial point for this vector is -3, 2, which would be right over here. This is our initial point. And our terminal point, and I'll just do that in a different color, would be the point 4, 1. That's our terminal point here. This was our initial point. And our vector then has this distance. This would represent our distance, but also our direction. And that's what's neat about a vector, is that it gives us both of those pieces of information. Now, most of the vectors that we work with are often described in something called component form, which is a way of pretty much just taking this vector here, and I'll just copy this, taking the same vector here and treating it as if its initial point was at the origin here. So we would have something like this. Well, how could we find that component form of that vector? Well, we would see that if this is my x1 and my y1, this is my x2 and my y2, so my horizontal and vertical components, we can just go ahead and write this vector. So I'll just say vector v here. We can describe it as x2 minus x1, comma, y2 minus y1. So what would that look like here? We would say that that is equal to, in this case, 4 minus -3, so 4 minus -3, and then 1 minus 2. And so all of that comes out to the following component form, 7, -1. And so we'd see here that this vector is equivalent to the vector that ends at the point 7, -1. And that seems to be pretty close to what I've drawn there. So there we have that. Now let's talk about a vector's magnitude. And I want to discuss the magnitude first because we're going to need that magnitude to write our vector in trigonometric form. So the magnitude is essentially just the distance or the length of our vector here. So how do we find distance? Well, we just use the distance formula. So we would say that the magnitude of our vector, so this is the notation for a vector's magnitude, is really, if we're just applying the distance formula here, what did we say that our horizontal distance was? Our horizontal distance here, we know is 7, so we'd say 7 squared. And our vertical distance here is -1, so we'd say plus -1 squared. So that comes out to root 50, which we can then simplify as 5 root 2. And so in general, a vector's magnitude we know is simply the following. It's just the distance formula using our horizontal and vertical components. Now that we have our vector's magnitude, let's use it to write our vector in what we call trigonometric form, which effectively just means we're going to do the following. We're going to write this as the unit vector's magnitude, or the magnitude of that vector, times the unit vector. And a unit vector is simply a vector with a magnitude of 1. So we can describe that, by just writing the vector divided by its own magnitude, or we can also write it in trigonometric form. So in this particular case, I'm going to say that the magnitude of my vector, which we said was 5 root 2, times the following. We're going to write this as, well, actually, I'm going to say the cosine of my angle theta times the sine of my angle theta. This is going to give me my unit vector here. Now, the thing that's missing then is I need to know what my angle theta is. What is my direction angle, if you will? So that's describing this angle here. That's my angle theta. Well, just look at what I've drawn out there. How would we find that angle? And the answer is we would use the inverse tangent function. We would say the arctangent of y over x, so -1 over 7, and that gives me -0.1419. That's in radians, or -8.13 if you're working in degrees. Either one of those work. So what we're going to do is we're going to just pretty much replace theta now for each of those. So I'm just going to go in here and replace those. So we're going to say -0.142, -0.142 if I'm just working in radians. So that is my unit vector. Now I multiply it by its magnitude, and that gives me the same vector now that it's written in trigonometric form. Now, finally, equivalent vectors, well, I already kind of touched upon this when I talked about a vector being written in component form. But the idea is, can you come up with a vector that may have a different initial and terminal point, but still has the same component form? So pause the video and see if you can think of an equivalent vector here, something that has the same direction and the same magnitude. And there's an infinite number of answers that you can come up with here, but for example, you might say something with an initial vector of, or initial point of negative 2, 2, so something like this, negative 2, 2, and a terminal point of 5, 1. So something like that would look somewhere right around here, okay? Now this is not going to be precise, but actually it's not bad. It's pretty close. Something like that. That's pretty good. Okay, so there's my equivalent vector there. So that's a quick recap of vectors and just some reminders on how vectors work and some important notation bits. Now let's move on to talking about vectors as functions, or vector valued functions. So I mentioned earlier in the video that that vector valued functions effectively work like parametric equations. So we are going to use these to give ourselves some information about things like the position, the velocity, and acceleration, all concepts that we've covered in this course. So in the context of vectors, let's start talking about things like the position vector. Well, the position vector we know is just going to be a vector defined as our parametric equation x of t being our horizontal component and y of t being describing our vertical component. And again, this is going to give us the location of a particle as it moves around the curve, right? So position vector gives us the location. Well, what about the velocity vector? The velocity, if you recall, is simply the derivative of the position. So we would say that this would be x prime of t and y prime of t. And again, this is going to give us the speed. And here's a clear or an important distinction. It's not only our speed, but it's our speed with, and I'm going to underline that, with direction. Okay, because without direction, we're just describing the speed, and we'll talk about that in just a moment. And finally, the acceleration we know is the derivative of our velocity vector. So this is x double prime of t and y double prime of t. So that's our acceleration. So now let's move on to talking about speed. Well, I just said that speed is simply the velocity without direction. So in other words, we're describing the magnitude, I'll write this down here, the magnitude of our velocity vector. And if you recall, the magnitude is effectively then just using the distance formula here. So we would say the magnitude of our velocity vector, we would say then is x prime of t, all of that squared, plus y prime of t, all of this squared, okay? The distance that a particle travels along a plane curve, we can't just use the distance formula because oftentimes these are curves, so we're going to want to use our arc length formula. So we would find the integral from a to b, so given our parameters and where we're integrating from, this is going to then be the square root of x prime of t plus y prime of t squared, all of that dt. And again, all of this is just the integral of our speed vector, or the integral of our speed, if you will. Okay. And now, finally, and this is just review. When is a particle at rest? Well, we know a particle is at rest when our velocity is equal to 0. So we'll just set our velocity vector equal to 0. Okay. So with that said, take a moment, jot those down, and let's try a practice problem as we work through this. Take a moment and pause the video right now and go ahead and graph those parametric equations and find what your plane curve looks like. And make sure that you're in parametric mode and that your window is set from 0 to 2. And if you do that, then you should get something that looks roughly like this. This is just kind of a rough sense of the plane curve here. And you should see using these arrows that they're moving in this direction. And this is when t is equal to 0. And you'll see that this also is at the point when the y-axis is 4. So it should look something like that. Now that we see our plane curve, let's find the velocity vector. we would see that our velocity is simply then the derivative of our position vector, which is given to us. So velocity then is the derivative, let me just write that, the derivative of our position vector. So we would say this is going to be the derivative of 3t squared is 6t. 3t squared minus 6t is our vertical derivative. And we're now going to evaluate this velocity vector at 1. In other words, what is the velocity vector when t is equal to 1? So plug in 1 there, we just get 6 comma negative 3. All right, now let's talk about the speed of the particle. Well, very much related to the velocity. If we know the velocity at t is equal to 1, then the speed of that is simply the non-vector form, or the magnitude. Let me write that, the magnitude of the speed, which is just going to be 6 squared plus negative 3 squared, and then that's equal to root 45. And if you want to clean that up, you can say that that is 3 root 5. All right, now let's look at the distance traveled between t is equal to 0 and t is equal to 3. I know this t is equal to 3 is beyond what we graphed, but I think we can still do it without it. So think about what that would look like. We would find the parameter, or excuse me, the integral, from 0 with the parameter up to 3 of our speed. So we're going to integrate our speed. That's going to give us our arc length. So we would say 6t squared plus 3t squared minus 6t, that entire quantity squared, all of this with respect to t. And if you punch that into your calculator, you should get approximately 28.583. Next up, when is our particle at rest? Again, when our velocity is equal to 0. So we're going to take our velocity function that we have here, we're going to take this, and we're going to set it equal to, whoa, messing around with the size there. All right, we're going to set this equal to 0. So we would have the following. 6t is equal to 0, which means t is equal to 0. And then take this component and set it equal to its vertical, when the vertical component is equal to 0. So 3t squared minus 6t is equal to 0. If we factor that out, we get t minus 2 is equal to 0. So t is equal to 0 and 2. The time when the particle is at rest is when both the vertical and your horizontal components are equal to 0. That would mean, let me highlight both of these, that happens here. So we would say that our particle is at rest when t is equal to 0. And finally, what is the acceleration vector at time t is equal to 2? Well, we would say a of t is equal to 6t minus 6, and which is just the derivative of our velocity vector again. And we're going to evaluate that at t is equal to 2, which means we just get 6, and 12 minus 6 is just 6. So we get that there. Okay? I'm going to now encourage you to go ahead and try this next problem on your own. And I have the solutions posted. It's going to be a pretty similar problem, but this time notice that I'm starting out by giving you the acceleration vector. So what does that mean if we're going to need to find things like the velocity and position vector? Well, we're going to need to integrate. And I think you can figure out the rest of these parts. And again, you can check your solutions with what I have uploaded. But I want to move to number 3 real quick. Not a super long problem, but I do want to kind of go over it. So we have a particle that is moving around the curve that is defined as r is equal to 2 sine theta, such that for any time t, theta is equal to 2t. So in other words, when t is equal to 1, we would say theta is equal to 2 times 1, or 2 radians, if you will. So theta is a function of t, if you will. So we're going to need to find our particle's position, velocity, and acceleration vector. And then we're going to want to find the total distance that this particle moves around this curve from 1 to 2 inclusive. So we're going to start off by writing our x and y equations. So we're going to say x is equal to r cosine theta. So in this case, it's 2 sine theta times cosine theta. And if you want to, you can use a double angle identity here to rewrite this as sine of 2 theta. That just might make your life a little bit easier when we're differentiating later. When we have to differentiate this, it might be nice to just have everything in terms of sine instead of having to use the product rule, but it's completely up to you. Next up, we're going to write our y equation. So y is equal to 2 sine theta times sine theta, right? This was r sine theta times sine theta. So y is equal to 2 sine squared theta, okay? So now we're ready to write our position, velocity, and acceleration vectors. We're just going to be differentiating here. So first off, our position vector in terms of theta is the following. 2 sine theta cosine theta, or actually maybe let's just write the double angle form of it. We're going to just write sine of 2 theta. Our y component is 2 sine squared theta. When you're working with double angles, just make sure you're super careful with how you write your coefficients and your exponents. But now we want to rewrite this position vector in terms of t. We want to write it in terms of t. So we're going to rewrite this as the sine of 2 times theta. And if theta is equal to, what is theta equal to? 2t. Well, all of this is just equal to, and I'm just going to clean this up here, write this as 4t. And then this is 2 sine squared 2t. So there's our position vector in terms of t. To find our velocity vector, we're now going to differentiate. So we're going to apply the chain rule here. So we're going to say 4 cosine 4t. And if we do the chain rule to this part here, you may want to rewrite this as just 2 sine of 2t, all of this squared, if that makes your life easier. But you're going to want to, after you do some differentiating and apply the chain rule, you're going to get 8 cosine 2t sine of 2t. And if you want to, you can indeed use a double angle identity here to simplify that again. So cosine of parentheses around that, 4t, 4 sine of 4t. I'm just applying a double angle identity again here. Okay, so this is just a double angle identity again. Double angle. All right. And finally, not finally, we got one more thing after this, but the acceleration vector is going to be the derivative of all this. So we have negative 16 sine 4t, and the derivative of the y component is going to be 16 cosine 4t. All right, so we've got all three of my vectors. Now it's asking us for the total distance that the particle travels between 1 and 2. So the distance is going to be the integral. So we're going to use our arc length here from 1 to 2. And it's just, we're going to be integrating our speed, which is 4 cosine 4t. So basically our vector, velocity vector without the direction. So just the magnitude of our velocity. You're applying the distance formula to all that. And you could probably do this mentally. Just think about that for a second. But if you can see what's happening there, hint, you are using a Pythagorean identity. This should come out to 4. And that's the distance of your arc length.